So even though we have not been very far into the Earth's crust as far as how far we've been able to dig, we do understand what the other layers are made of. And one of the biggest ways that we know this is through seismology. When an earthquake happens, it sends shock waves throughout the planet. Seismologists record these vibrations, and it's almost as if we hit one side of the planet with a gigantic hammer, and then you listened to it on the other side for the noise. Depending on the routes these vibrations take, they pass through different bits of the Earth, and it affects how they sound at the other end. Early in the history of seismology, it was realized that some vibrations were going missing. These S waves were expected to show up on one side of the Earth after originating on the other, but there was no sign of them. The reason for this was simple. S waves can only travel through solid material and can't make it through liquid. So they must be coming up against something molten in the center of the Earth. By mapping the S waves' paths, it turns out that the rocks became liquid around 3,000 kilometers down. That suggested that the entire core was molten, or liquid. But there was another surprise in store. They found another kind of wave which are called P waves, and these unexpectedly traveled through the core and could be detected on the other side of the planet. And here was the explanation. The core is divided into two layers, the inner core and the outer core. The inner core was made of a solid, and the outer core was made of a liquid. This is why we were able to tell that S waves, when they came in contact with the liquid outer core, refracted or bent away because they couldn't travel through. P waves, however, did travel all the way through, but the scientists or seismologists noticed that they refracted and bent every time they hit a new layer. So when we're taking that information and we're applying it to this map or this graph, it's important that we understand what it's showing. First of all, over here on the side, it's showing depth. So we're starting up here at the Earth's surface or the crust, and you can see that's labeled at the top. And as we move down, we're going deeper towards the inner core. The numbers up here are the velocity, also known as speed with direction. So in this case, just specifically think about speed. So if you look at how these waves are traveling, there's two different types of waves that happens when an earthquake occurs. One of them is the S wave. What you can see is every once in a while, this wave, it picks up speed, and then all of a sudden it changes very abruptly. What this means is that it's contacting a new layer. So you can see up here was the lithosphere. It traveled. Here's an abrupt change. That was the asthenosphere. Here is another abrupt change. So this large section right here represents the mantle. If you continue to follow the S wave's path, all of a sudden it hits here and it just disappears. This is one way that we know that the outer core is made up of a liquid. So scientists knew that there was a different material that was making it up because all of a sudden this wave just disappeared. It couldn't travel through it. So in this case, where it says, why did the S waves stop at a depth of 2,900 kilometers, it's simply that S waves cannot travel through liquids. Now we're going to look at the entire thing and try to find two statements that are true regarding the diagram below. So first of all, the first one says, seismic waves are refracted or bent when they entered a new material. As we talked about on the previous slide, we can see that already. So as soon as it hits the asthenosphere, it changes directions. It hits the mantle, it changes directions. All of a sudden it's picking up speed, and then it hits a new layer and dramatically decreases speed. It goes from a 12 pretty much always to an 8. So we're going 12 kilometers per second, and now all of a sudden we drop to 8 kilometers per second. So now we're in the outer core. And again, it's gradually picking up speed, and then all of a sudden abrupt change. Okay, and that's when we hit the inner core. So we do know that they're refracted or bent when they enter a new material. Next one says, P waves decrease their speed as they make their way to the core. Well, not necessarily. Here they picked up speed, then it dropped. So it went from a 12 to an 8. Then it picked up speed. So it does not consistently decrease or increase as it's moving through. So it can't be B. Next it says S waves move faster and farther than P waves. Well, we see that S waves already stop right here. So we know that they definitely don't travel farther. Finally, it says P waves travel with more energy than S waves. I would just think of more energy as being able to travel farther, that they can do more, and that's exactly what P waves are doing. So in this case, the answers would be that seismic waves are refracted when they enter new material, and P waves travel with more energy than S waves.